Hey guys, today we're going to start talking about ions. This is definitely something you've seen before. Kind of my hope is now it's a little bit more clear and we have maybe a better understanding overall of how ions work, just because we're going to use that knowledge of ions as we move forward to talk about things like ionic bonds, ionic compounds, and then we'll also talk about things like covalent compounds. The main thing we want you to get out of today is understand the difference between an atom that's reactive and an atom that's non-reactive, and kind of understand what makes an atom reactive and what does that have to do with stability. So that's going to be the hope today, and then we'll use our understanding of things like charges and where charges come from to help do that. So ion formation, let's go. Okay, so brief review here. Ions have the same number of protons, different number of electrons. So here I have two atoms. You'll notice here that the electrons, the little red things on the outside, are the same as my number of protons here. So I have 9 dots and a 9 plus. 9 electrons, 9 protons. Over here, 10 plus and 10 electrons. So these are both called atoms because they don't have differing numbers of protons and electrons. You would have to answer the question, what atom is this? In order to do that, you would have to look on the periodic table. So if we look at it, we'll see things like fluorine, which has 9 protons. That's where the 9 comes from. And neon, which has 10 protons. That's where the little 10 comes from. Now, we know by looking at our periodic table that fluorine has 7 valence electrons. And looking at this drawing here, we can see that there's 7 dots on this outermost circle. And the same thing with neon. We know that neon has 8 valence electrons. And we can do that just by looking at the periodic table or by looking at these dots around the outside. Now, here's how this comes into play. One of the things we told you about families is I said everything like fluorine, every single halogen is very, very reactive. That's true for fluorine, that's true for chlorine, that's true for bromine. All the halogens are all very reactive. With neon, neon's an example of a noble gas, and noble gases really aren't reactive. So things like neon, argon, helium, not reactive at all. Now, it's interesting that they have similar reactiveness and the exact same number of valence electrons, exact same reactiveness and exact same number of valence electrons. So, one question that I hope you guys have been thinking about is, hey, how do valence electrons influence reactivity? And the answer is a little bit complicated. The answer is the closer you are to stable, the closer you are to 8, the more reactive you will be. So if we're at 7 here, we're 1 away from getting to 8. But if we're further away, like let's say we're at 6 or we're at 5, we're going to be less reactive just because we would need to gain 3 electrons, for example. Now, this is tough because it doesn't necessarily mean that 7 is the most reactive and 1 is the least reactive, because it turns out that atoms can both gain or lose electrons. So if you're at 1, you would just lose 1 electron and then you'd get back to 8. So it doesn't necessarily look like a number line 1 through 8. Instead, what it looks like, oh, sorry, I'm not on that page quite yet. Um, Instead, what it looks like is going to be more like a clock, and I'll show you that in a little bit. Okay, so anyways, valence electrons, remember, that's a full outer shell, gives you a stable atom. So if you have a full set of valence electrons, that can either look like 8 valence electrons for most atoms, or sometimes things like helium and lithium and beryllium, they're stable when they only have 2 valence electrons. But those are kind of weird exceptions that we're really just going to focus on this idea here that 8 valence electrons is stable. And then again, like I said, the closer you are to stable, the more reactive you would be. That's a takeaway from today. So I would definitely have that somewhere written down in your notes. Um, the best way I can compare it is like if you're very close to school and let's say you're late, you're going to run faster, right? So if you're like 50 feet away from the classroom door when that bell rings, you're going to sprint to class, right? But maybe if you're 500 feet away, that's you can't sprint 500 feet unless you're like super, super good. So maybe you might jog. And then if you're like a mile away from class and you're late, you're not going to sprint a mile. Or maybe you will. but you'll probably just walk to get to class. And it doesn't matter if you're on the left side of the classroom or if you're on the right side of the classroom. Either way, it's kind of the overall distance you are away from the school that'll determine, not if you're on the left or the right side. So hopefully then you can see how I'm going to try and compare this to ions, meaning if you're close to 8, you might sprint to get there. You might be very reactive. Or if you're further away from 8, you might kind of jog to get there because you're less reactive. But if you're on the left side, you might lose electrons, or if you're on the right side, you might gain electrons. So like I said, it's less like a number line, and it's more like a circular kind of clock shape. So let me show you what I'm talking about with that. Here's my clock, but instead of the numbers being 1 through 12, I've changed the numbers to being 1 through 8. And kind of the idea is the closer you are to 8, the more reactive you will be. So the question is, which hand is the closest to 8? Well, which number is closest to 8? Honestly, it's probably a tie between 1 and 7, first off, because they're kind of one step away from getting to 8. Right? So 1 valence electron and 7 valence electrons are both 1 valence electron away from 8. If you gain 1 from 7, you get to 8. Or if you lose 1 valence electron, you go back to the next level, which should be full. So either way, you get to 8. The same thing is true for 6 and 2, right? If you're 2 valence electrons away from 8, you could gain 2 or you could lose 2. And either way, you'd kind of get back to that 8 starting point. And then for 3 and 5, you're 3 valence electrons away. And with 4, you're 4 valence electrons away. Now, 4 is kind of tricky because it could, again, gain 4 or it could lose 4. So honestly, if you have 4 valence electrons, you're like, there's no way I'm getting 4 valence electrons. That's going to take forever. So things with 4 valence electrons tend to be really unreactive just because they're like, maybe I'll get an electron, but I probably won't. Versus like if you have 1 valence electron, you're going to be like, oh, I'm so close. I just need this one more valence electrons to do the thing. Kind of like if you're super behind in a game of Monopoly, you're like, I don't really even care about this game anymore. Versus if you're super close to winning, you're going to be way more into it, way more reactive, perhaps. Okay, so this is kind of a bizarre visualization. Let me take this clock metaphor and then put some atoms next to it so you can kind of see where I'm coming from here. All right, so on the left side here, we've got an atom that has 7 valence electrons, so you'll notice 7 dots around the outside, total of 9, keep in mind. And then on the right side over here, we've got 1 valence electron. So in both these cases here, they're 1 valence electron away from 8. Let me show you what I mean. With 7, of course, you gain 1 electron, and when you do that, I'm just going to pop in an electron right there. Wha-bam! Now notice we're at 8. 1, 2, 3, 4, 5, 6, 7, 8 around the outermost energy level. If I have 1 valence electron, though, and I lose it, so I'm just going to do that with the red valence electron. Well, bam, there, it's gone. Now, looking at this second level, notice that it's full. So now I have 8 once again. That's pretty awesome. So both of these, with 7 valence electrons and with 1 valence electrons, you're equally far away. So elements with 1 and 7 valence electrons are going to be equally reactive. They're going to be equally interested in becoming stable. So those atoms are, or those ions are super, super reactive because they want to form, or sorry, those atoms are super reactive because they want to form these ions where they get to a stable 8 valence electrons. On this next one, I've got an atom on the left that has 6 valence electrons. 1, 2, 3, 4, 5, 6. And then over here, 2 valence electrons. Again, very similar things going to happen here. We'll notice 6 valence electrons is going to gain 2. There they are in green. And in red here, we're going to lose our 2 electrons. Again, they're both at 8. And notice that they have the exact same number of electrons now. Kind of cool. We can do the same thing with 3 and 5. Here's my 5 valence electrons. So I'll gain 3. Well, bam, there's 3. And then I'll lose 3 on the other side. There I go, lose 3. Again, notice total number of electrons now that they form their ions. Exactly the same. That's the key here. And then lastly, with 4 valence electrons, either one of these could gain or lose 4 electrons. I'm just going to show the left one gaining because that's what I've been showing, and the right one losing. But you could also have this right one gain another 4 electrons if it wanted to. But either way, what you'll notice here is that they'll always end up with those 8 valence electrons and be nice and stable. So that's great. That's what we're looking for, right? And again, keep in mind, I'll say that 4-valence electrons is tricky because they're so unreactive. Usually they won't form ions. Usually instead they'll share, which is something called a covalent bond, which is something we'll eventually talk about in this class. Get excited for that. Okay, so what I've created here is this little ionization table where I'm going to show you what the reactivity of each and every single atom is based on their number of valence electrons. We're going to show you how that affects the number of protons and the number of electrons once it's formed an ion. Here's a hint, protons won't change. We're going to show you how that determines the charge, and we're also going to show you, okay, we start with 1 valence electron, but what number of valence electrons do we end with? So I wouldn't expect you to write this down, and this is going to be a lot of information. What I want you to do from this is kind of look to find patterns. So here we go. 1 valence electron is very reactive, but as we become with 2, 3, and 4, you'll notice that the reactivity is dropping from very to somewhat to slightly to not very reactive. And this is a true fact. A 2-valence electron atom is less reactive than a 1-valence electron, and 3 is way less reactive than 1 as well. Now, remember, 4-valence electrons can gain or lose. So I'm writing down 4 twice, meaning that this red 4, they're going to lose 4 electrons, and this green 4-valence electrons, they're going to gain 4. What I hope you notice is as we go from 4 to 5 to 6 to 7 to 8, just like that clock metaphor, these guys are going to become more and more reactive until we hit 8. And once you have 8 valence electrons, you're stable. So that means you're not reactive at all. No reactivity whatsoever because you're stable. Now, let's talk about changes in electrons here. With 1 valence electrons, remember, we lose 1 and then lose 2, lose 3, or lose 4. And then once we start looking at the green stuff here, we're going to add 3 or add 2 or add 1. Or in the case of 8 valence electrons, there's going to be no change. You don't add anything. You add 0 or you remove 0. Notice here how the fewer number of electrons you add, for example, adding and removing 1, the more reactive you are. So our most reactive substances have the fewest change in total electrons to become stable. So that's one takeaway here. That's kind of the second takeaway of the day. The fewer electrons we have to add or remove, the more reactive an ion becomes. Or actually, that should say atom. The more reactive an atom becomes because it wants to become an ion. So let's just say, for example, this is the number of protons atoms might have. This is just something from your periodic table. If you have 11 protons, you have 1 valence electron. 12 has 2, 13 has 3, 14 has 4. Notice that this is the same atom here. In both cases, this is silicon. And then 15, 16, 17, 18 have 4, 5, 6, 7, and 8, respectively. So what's going to happen, though, is for 11 protons, we're going to lose 1 electron. So it should be 11 and 11 when they're an atom, but then if we lose 1, the number of electrons here is going to be 10, right? 12 and 12, but if we remove 2, it's going to be 10 again, right? Oh, and then the charge here for sodium would be 1 plus. Sodium is the atom with 11 protons. And then again, we lose 2. The charge here is going to be for magnesium 2 plus, because 12 minus 10 gives you plus 2. For 13, we're going to remove 3. So we have 13 and 13, remove 3. Once again, we're going to have 10. Notice what's happening here with our total number of electrons. It's pretty constant, right? Now, that's going to be different once we're starting to add electrons. 14 and 14, but add 4, and we're going to get 18. 15 and 15, but add 3, we're going to get 18 again for all these other ones, right? And that forms things like phosphorus, sulfur, 2 minus, chlorine 1 minus, and argon 1 minus. Now, something that's interesting about 10 electrons and 18 electrons is that is the number of electrons that for 10 is the number of valence electrons neon has, or sorry, total number of electrons neon has. Neon is 1 noble gas. 18 is the number of electrons that argon has. Argon is another noble gas. Both argon and neon have 8 valence electrons because they're in that noble gas column 18. So if we have 10 electrons, we have 8 valence electrons. If we have 18 electrons, we have 8 valence electrons as well. So every single ion always has 8 valence electrons, unless it's something like hydrogen or lithium, where they have 2 valence electrons to be stable. But for the most part, every atom we're going to work with is going to want to get to 8 valence electrons. So that's our third takeaway of the day. All ions have the same number of valence electrons, meaning they all have 8, except for, again, lithium and then beryllium. They'll have 2 just because they're weird. All ions have the same number of valence electrons, and they'll also have a similar number of total valence electrons. So for total number of valence electrons, you're looking at numbers like 2, which is heliums, 10, which is neons, 18, which is argons. So they will have like a noble gas amount of total electrons. 8 valence electrons, there's only a couple ways to do that. You can either have 2, 10, or 18 is kind of the idea there. Okay, so taking a look here, notice that, okay, so here's kind of a visualization of stuff. We have 2 electrons in our first row, and we have 8 electrons in our second row. So that's the total of 10. This would be the same number of valence electrons as a neon atom would have. If we have 7 protons, the first question is asking, what is this atom called? So this atom would be called nitrogen, right? Nitrogen's got 7 protons. But then notice here that it's got a total of 10 electrons. So the charge of the ion would be -3. And then over here, 13 protons, that's aluminum. The only way you know that is by looking at the periodic table. And then in this case, 13 protons, 10 electrons. The charge here is going to be +3, right? Because +13 minus 10, +3 versus +7 minus 10, -3. So the question is, how are these two atoms similar? How are they different? Well, they're similar because they both have the same exact number of electrons. They're different in terms of number of protons, different in terms of number of charge, but they're also the same in terms of stability. Both of these have now formed ions, so they're stable. That means they're not going to react anymore. That means they're not going to accept any more electrons. They're not going to remove any more electrons. Just to clarify here, in green and in red, I showed you kind of, oh, these are the 3 electrons that aluminum lost, or these are the 3 electrons that my nitrogen over here gained, for example. Hopefully this helps understand, make it a little bit more understandable, kind of the difference between an atom and an ion. And the main takeaway here, guys, is this. Every ion will always have 8 valence electrons, except for lithium and beryllium. Those two have like 3 total electrons and 4 total electrons, so they'll go down to 2, which is helium. And then keep in mind that the fewer number of electrons we have to add or remove, the more reactive an ion becomes. It's easy to kind of view this like a clock almost, where, in each case here, we're either gaining or losing 1, gaining or losing 2, gaining or losing 3, or gaining or losing 4. I hope this helps. I hope you have a better understanding of ions at this point in time, and I also hope that you have a wonderful rest of your day. Take care.